Welcome to the wonderful world of physics. This is the Chapter 18 homework for Physics 102B. We start with question number 5. A negatively charged particle is moving horizontally in a region with a magnetic field directed vertically upward. Describe the particle's motion. So here I've drawn the magnetic field being drawn out of the page, and there's our field. We're going to use the left-hand rule, and we see that it goes horizontal and in a circle as I've drawn there. Number 8, does the magnetic force ever do work on a moving charged particle? Or remember back to last semester, work is equal to the force applied times displacement times the cosine of the angle between force and displacement. However, the force is always going to be perpendicular to displacement. And so because of that, there's a 90-degree angle. Cosine of 90 degrees is 0, and therefore work is always going to be 0 by the magnetic force. Number 15, a wire carries electric current horizontally from west to east. So right away I've drawn the compass directions there as if drawing a map. And I've drawn the wire going from west to east, from left to right. In what direction should a magnetic field point so that the force on the wire is vertically downward? So I've drawn the force going into the page. That would be downward on the map. You're going to use your right hand and point your outstretched hand and fingers towards the right. Your thumb points into the page, and when your fingers curl at a 90-degree angle, they point down, which is in the southward direction. Number 23, a negative particle traveling northward is deflected toward the east by a magnetic force. The direction of the magnetic field is, and it gives multiple choices. All right, so since it's a negative particle, we're going to remember to use our left hand, and let's draw what's given here. It says it is deflected toward the east, so I've drawn the force to the right. The direction, it's traveling northward, and so I've drawn it in the light blue going north. So I'm going to take my left hand, because it's a negative particle, point my hand and fingers up on the page. My thumb goes to the right, as you see there, with force. And then when I curl my fingers at a 90-degree angle, it goes into the page, which on a map would be down. Number 25. A negative 50 microcoulomb charge moves vertically upward at 75 meters per second. Which magnetic field will produce a northward magnetic force of 15 millinewtons? And we're given our choices of either 2 Teslas east or west or 4 Teslas east or west. Since it's a negative charge, we're going to use our left hand, and we have the equation force equals charge times velocity times magnetic field times the sine of the angle, and the direction between velocity and magnetic field is perpendicular, so the sine of 90 degrees is 1. We have F equals QVB. And for Q, notice that it's the absolute value sign, so we're not going to use the negative in there. We solve for B, and we get 4 Teslas. Now, as for the direction, we want to know the direction of the magnetic field. And so we'll point with our left hand coming out of the page, rotate so our thumb can point upwards as you see the force drawn, and our fingers should curl to the left, which is the westward direction. Number 35, a 0.95 Tesla magnetic field points due north. And there you can see I've drawn it going north. Find the magnitude and direction of the force on a 1.4 microcoulomb charge moving westward at 1.5 meters per second. And there I've drawn it going west. So you should use your right-hand rule on this positive charge and get the force going into the page which is going to be down. Use the equation F equals QVB sine 90 degrees, and that gives you 2 micronewtons, and that's down. For the negative charge, you can use the left hand, or you can just say that it's going to be opposite of the force that would be on a positive charge, so 2.0 micronewtons upward. Number 37. A 1.5 Tesla magnetic field points northeast, and you can see in my various diagrams it's pointing northeast at that 45-degree azimuth. Find the magnitude and direction of the force on a 0.5 Coulomb charge that is moving 10 meters per second toward these different parts, northeast, southwest, and southwest. And again, we want to find the magnitude and direction. So for part A, where it's going to the north, we can do QVB times sine of, you can see a 45-degree angle in there, so we plug in the values and we get 5.3 newtons. We're going to use our right-hand rule, and so point our hand in the direction of velocity, allow fingers to curl in the direction to the upper right, and then you get your thumb pointing into the page. So that would be on a map direction into the page would be down. For part B, going to the east, so you can see the vectors I've drawn, the right-hand rule should give you the force coming out of the page. And when you do the equation, 5.3 newtons, and that would be up. For part C, now it's going to the south. We draw the picture, use the right-hand rule. The force goes out of the page, which is up, and we plug in the values. And now it's a sine of 135 degrees. That's actually the same of 45 degrees. And so it gives the same quantity as parts A and B, so 5.30 newtons. Part D, it's moving to the west. There I've drawn the picture. I apply the right-hand rule. The force is going into the page, which is down. Once again, it's 5.30 newtons. And finally, to the southwest, you can see by the picture the magnetic field and velocity are anti-parallel to each other. There's a 180-degree angle. The sine of that is 0, so the force is 0. Number 38. A negative 200 microcoulomb charge moves vertically downward at 12.3 meters per second. Find the magnetic field required to produce a northward magnetic force of 1.4 millinewtons. So we're going to draw a picture. We have it moving vertically downward. I've got that into the page. And we want a force that is northward. So we're going to use our left hand because it's a negative charge, and a left hand with our thumb pointing upward on the page, hand going in to the page, and our fingers should curl to the right, as you see in the picture here, and so that would be to the east. Now we're going to use the equation F equals QVB sine theta, and you solve for B, plug in all the values, and you get 0.569 Teslas eastward. For number 41, I have this negative charge moving in the positive y direction, as you can see my velocity vector. Magnetic field is in the negative x direction, as you can see in the picture. The magnitude and direction of the force on the electron. First, we're going to use the left-hand rule because it's negative, and you should get that the force goes into the page. Now, if up is positive y and to the right is positive x, then coming out of the page would be positive z. Since it's going into the page, that's the negative z direction. Force equals QVB sine theta. And so you should plug those in and get 1.1 times 10 to the negative 13 newtons. For part B, find the electric field that would give zero net force on the electron. So now we're going to balance that magnetic field with an electric field. The electric field is the force divided by the charge, or the absolute value of the charge. And so we have the force from part A, divided by the charge on the electron, we get 6.8 times 10 to the 5th newtons per coulomb. And then we want to think about the direction that that electric field should go. And so to force a negative charge in the positive z direction, the electric field should point in the negative z direction. Number 43, a proton moving in the positive y direction, as I've drawn there. The uniform magnetic field is in the positive z direction, so coming out of the page. Find the electric field that must be applied to give zero net force on the proton. So the electric field needs to point in the negative x direction. The reason is, if you use the right-hand rule, you can see, as I've drawn in the diagram, that the magnetic field is pointing it in the positive x direction, pushing it in the positive x direction. So the electric field needs to push it the other way. Now we need a balance between these two forces. Magnetic force equals electric force. So we have QVB equals QE. The Q's divide out, and you're left with an electric field being equal to V times B, so 4,500 meters per second times 0.450 Teslas. And so we get an electric field of 2025 newtons per coulomb. For number 46, we're looking at a mass spectrometer separating uranium isotopes 235 and 238. What is the ratio of the radii of their circular paths? So we'll do part A first. There's the equation that we derived in class, and it's in the textbook. The radius is, and it says what is the ratio of those radii. So let's make a ratio there. The radius of the 238 isotope over the 235 isotope. We need their masses, and the mass of uranium-238 is 238 atomic mass units. The mass of the 235 is 235 atomic mass units. The atomic mass units just divide out. And so it's a ratio of masses of 238 to 235. So here I've drawn, or I've written the radius of 238 in black, and I'm multiplying by the reciprocal of the radius of the 235 in blue. A lot of things cancel out, and all we're left with is the ratio of the masses, and it comes out to be 1.013. Now for part B, it says singly ionized uranium ions pass first through a 140 meter per second velocity selector and then into a 2.75 Tesla magnetic field. Find the diameters of the arcs traced out by the two isotopes. Well, here we're given their speed. We want to know the radii. And F equals ma, going through a magnetic field, gives us QVB equals mv squared over r. So radius is mv over qb. The radius of the 238, we can plug in all these values. We have 238 atomic mass units. We need that in MKS units, so let's multiply, convert it to 1.661 times 10 to the negative 27 kilograms over U. And we've got the speed, we've got the charge. It says it is singly ionized, which means it has effectively the charge of a proton, and the magnetic field, and you get 1.256 times 10 to the negative 4 meters. The question is asking about the diameter, so we're going to double that. We get 0.251 millimeters. We go through the same procedure with the uranium-235, and we get a diameter of 0.248 millimeters. Number 59. A copper wire has diameter 0.15 millimeters, length 10 centimeters. It's in a horizontal plane and carries a current of 2.15 amperes. Find the magnitude and direction of the magnetic field needed to suspend the wire against gravity. So we can draw a force diagram on this wire. Gravity's pulling it down. The magnetic field is going to balance that. And so that's I times L times B. And so if these forces are balanced, then ILB equals mg. We can solve for the magnetic field. Now we have to figure some things out here. So the mass, we don't directly know the mass, but it mentions that it is copper. And so we can get the density of copper. Mass is density times volume. So I'll turn mass here into density times volume. And since it's a wire, which is basically a long, thin cylinder, volume becomes pi r squared times the length. That would be the volume of the wire. And you can see that length divides out, and we're left with that the magnetic field is the density of copper times pi r squared times G divided by the current. And then you can plug in all the values and you get a magnetic field of 718 microteslas that will suspend the wire. Number 71. An electric motor has 1500 turn, 15 centimeter diameter circular coil on its armature. Find the magnetic field needed to produce a maximum torque of 25 Newton meters when the coil current is 12 amperes. Well, we find the equation for that. The maximum torque on such an arrangement is the number of turns times the area times current times magnetic field. We're going to solve for magnetic field. For area of the circular coil, it's pi times the radius squared, which is pi times 0.075 meters. Square it, and in the end you should get 78.6 milliteslas. Number 72, a long straight wire with 2.5 amperes along the plus x-axis. Find the magnitude and direction of the magnetic field at A, a point 15 centimeters away on the plus y-axis. And so you can see on my picture, there it is. And part B, a point 15 centimeters away on the negative y-axis. So there it is. All right, so we're going to figure out actually, let's do the direction first. And using the right-hand rule that refers to the magnetic field produced from a wire, we're going to take our right hand and imagine that we are wrapping our fingers around the wire to hold the wire, and above the wire, our fingers point towards us. They point out of the page. If you continue curling your fingers around below the wire, they go into the page. So you can see my magnetic field at those particular positions. Now let's solve for the magnitude of a magnetic field that is produced by a current in a wire. It's mu naught, the permeability constant, times current divided by 2 pi in the distance. And you can plug all those values in, and you get 3.3 microteslas at that distance. And then we can say that based on our picture up above from the right-hand rule, in part A, it's in the positive z direction. So as a vector, we can write that as 3.3 microteslas k hat. And at part B, point B, it is in the negative z direction, so we can say negative 3.3 microteslas k hat. And that is the end of the Chapter 18 homework. Have a great day.